We'll use that time for something else. Okay. I'll probably go out. Okay. Yeah. So. People they
We are, yes.
Okay.
Yeah.
Thank you.
And then we that person on the rolls there, the bottom, it goes through the car.
But that's some coming days.
And then they just really small.
You cannot make this But she only does it when no,
So I just wanted some advice as we're working on a case for that arrow. And I talked to Mayor Al. Helping me a lot with OpenFOAM, but it's kind of more of a general question. Basically, I have a problem, and it's like it's a wing. This is a 2D cross section, but essentially, I had it working. I had a one element wing, and it worked. And I can tell because like the last 100 times that's what converged that they also coefficient. And the residuals went down and everything was cool. All I did was throw it in different geometry, and it started blowing up. And essentially, what would happen was like, I don't have the logs, but this bounding utilde number would just blow up, right? And so I figured if you have identical case and you just change the geometry, then it has to be a mesh issue, right? It's like I couldn't say that.
So everything else is the same.
Yeah, I changed everything the same. I just changed like the 2 files, the meshing files. I just changed the name. Obviously, put in a new OBJ or STL, and then I changed it to read that name of that file.
I see.
Like,
How are the geometries different? Is it
so they're actually the same. That was one of the things I did was like here in this file, in surface features, you set the angle to read. And so when I was looking at I was kind of visualizing the lines that it captured. I realized it wasn't capturing like all the lines, like the front of the airfoil, the leading edge, like it wouldn't capture it. So I just ended up upping the angle more and more until I thought that it captured a decent amount of lines. And I had thought that that was my solution, and it wasn't. And so when I've just been troubleshooting like over and over, and I'm kind of like getting burnt out of ideas. I talked to Dr. Mayorel the other day, and I found out that basically what I should have done was the refinement box that I made, I set it like right in front of the airflow. Because I looked at the bounding box of the airflow, and I basically set the refinement box like right there.
Okay.
And so he was explaining to me that the transition region was too short in cells that were trying to be generated to the nice refinement were being concave, because that's the only error I'm getting, which is concave cells.
So it's a dynamic mesh, the mesh is changing. That's why.
I'm not necessarily sure, but I can show you, but it sounded really nice, and so I changed the refinement box, it made it huge. And that was just the other day, and I didn't fix it,
So the cell, because if it's just a aerodynamics, I mean, the cell should be static.
yeah.
I don't think the cell should be. Okay.
Here, you can see here, this is this check, so this is the only critical error that it claims, which is concave cells writing 212. But mind you, the mesh check on the one that works gives the same error, you know, so.
Okay, and if it's the same one, if it's giving you the same thing.
But it's still running, and even like the solution shows, like the solution seems pretty stable.
Yeah.
On the forums, people say like, you can kind of ignore this because of the way, like, it's very strict mesh check.
I see.
But, yeah, and the boundary conditions, you know, I checked them with, you know.
I have.
What's your time?
So my time steps right now are just 0 to 500 and with the delta 1, and I know that can affect it. I haven't really played around with it too much. The only thing I did was make this 1,000 and make this 10.
Okay.
But if you think I should make them bigger or smaller,
So the delta T is the amount of time in between. And so usually when you're having like divergence issues or like the simulations going up, the first thing I usually try is actually lowering
lowering it.
Okay, so what could be happening, and what tends to happen is that you have a transient simulation, the delta T is too big, then basically you're taking snapshots of it. So in your case, you're taking snapshots that are 1 second apart.
Right.
So what can happen is that if the snapshots are kind of far apart, but the flow is like then the solver can get it.
It divides by 0 type of thing.
Not necessarily, it's just that the evolution, so basically the way the solver works is that it's between each time step. So it said, here's similar to 1 time step, and then it's similar to the next one. What it computes is, how is the solution evolved between them. So it's a rate change. Okay. But if it's going to evolve a lot, the rate of change that it really.
Yeah, right.
So that might cause, you might actually end up running into issues where the number's too big.
Okay.
So I would actually try to
make it half it, or what?
I would try start with half.
Okay. Should I?
It's interesting though, because like usually I'm used to like more smaller scale cells. Actually, my delta C's are actually on the order of like 1 million.
Yeah, they're really small, right?
So for aerodynamic, I know you're looking at.
Yeah.
I mean, I would try half. I would say in the most extreme case, I would try to still having that issue. I'll try that.
Okay, thank you. Yeah. Scale it. Yeah. Okay, awesome. I really appreciate it.
Okay. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Thank you. Appreciate that. Yeah, I saw Dr. Wang must be really confused because I got lunch with him earlier today and I had long hair, and then I saw him now and then I have short hair. And so, I'm sure he was confused, although he didn't tell me. So he's a nice guy. Okay. All right. And so today's actually going to be our first MATLAB workshop today. And so if you guys are here in the classroom, if you want to pull up one of the lab computers, you want to work on that, or if you're working on your own personal computer, that's good. So probably in the second half of the class, probably around maybe like 6:15, that's what I'm hoping for. We're going to develop kind of our first code together. Okay. All right. So today's exciting. So today, I think it'll be kind of a culmination of the last few lectures that we actually looked at, and we're actually going to do computational heat transfer, I think, for the first time today. Okay. All right. And so some announcements. I graded your homework ones just this morning, actually. And so, because I don't know if I mentioned this before, but because this is a technical elective, I grade the homework just based on completion. And so I didn't really leave any comments. I think a couple people, I left a couple comments and feedback if I saw something. But I'm mostly looking through just kind of fairly quickly just to make sure you did everything and you gave an honest effort. So, I forgot to post the solutions. And so, I think the danger with grading on completion is that it's kind of up to you guys to check the solutions. So just kind of make sure that every time I grade an assignment, I'll usually put the solutions on the same day, and so make sure you're checking the solutions to make sure that you got everything right. Okay. Homework 2, I should be posting that tomorrow, and so once homework 2 is posted, then you'll be able to work on that. Homework 2 is probably not going to be due until not next Friday, but the Friday after that. So it's a fairly big assignment. The reason I'm kind of waiting to post it a bit because a large portion of it is going to be this MATLAB stuff. And so I want to make sure we do a day of the MATLAB together so that you can kind of, so at least some of the homework will start to make sense. Okay, and so that's it for my announcements. Are there any questions, any other questions I can answer before we get started today? Thank you, appreciate that. Okay, all right, so let's go ahead and get started. And today what we're going to do is we're going to apply finite differences to the 1D diffusion equation. Okay. All right, so just a quick recap from last time. So if you recall from last time, we're primarily working on solving a diffusion equation in 1D, okay? And remember, the reason we're starting with this is that, in one dimension, we're able to solve these equations by hand. And so, when we start to write our code, we have something to check against. All right, so just to refresh your memory, so the equation that we're looking to solve looks like this. Okay. Right, so the main feature of this equation is that we have a second order derivative. So we have d squared phi dx squared multiplied by lambda there, which is our diffusion constant. Okay. And this is equal to some forcing function q. Okay, so very simple second order equation. And I believe we did an example last time. We solved it by hand. And the example was the following. And so our example was d squared phi dx squared is equal to 6x. Okay. And we had the following boundary conditions: phi of 0 is equal to 1. And then d phi dx at x is equal to 1 is equal to 0. All right, so last time what we did was we solved this equation by hand. And so solving this equation by hand gave us the following solution. So the solution to this equation is x cubed minus 3x plus 1. Okay. So for this example, we know what the exact solution is. And so this is the exact solution. Okay? And so what we're looking to do today is we're going to use finite differences and see if we can get this exact same solution using finite differences and using MATLAB. Okay, so that is the goal for today. Okay. Okay. So let's start, doing the finite difference process. Okay? So the first thing we have to do before we apply finite differences is we have to discretize our domain. Okay? And so this is basically going to take the same step as if you're familiar with finite elements, or if you're familiar with any kind of computational method. The first step you have to do is you have to mesh your domain. So you have to take your domain and kind of break it up into simpler shapes. Okay? And so, that kind of begs the question of, what exactly is our domain for this problem, right? And so, when you look at a differential equation like this normally, you don't really think about what's the problem domain, right? Because you're just looking to kind of solve the equation. But if you look at the boundary conditions of this, of our boundary conditions, that kind of gives you a hint about what our boundary domains are, okay? All right, so if we look at the first boundary condition, we can see that the first boundary condition is being applied at x is equal to 0. Okay. And if we look at the second boundary condition, Our second boundary condition is being applied at x is equal to 1. Okay, so those are kind of two different x locations. And so that tells us that, the left bound of our domain is going to be x is equal to 0, and the right side of the domain is going to be x is equal to 1. Okay? And so the way we can represent this mathematically is we can say that 0 is less than or equal to x, which is less than or equal to 1. Okay? It's a 1D domain because we're just solving kind of just a 1D equation. So if I were to draw the domain, it would look just like this. Okay. Our domain for now is just going to be a line. Okay. A line that goes from 0 to 1. And so we have to take this domain and we have to discretize it. Okay, so we have to break this up into kind of smaller segments so that we can apply finite differences to it. Okay. It may seem a little bit foreign, but after we kind of draw what the discretized domain is, it'll seem silly. Okay. And so if our whole domain here is a line and we want to break this up into smaller subdomains, then the way we're going to break this up is we're going to take our big line and chop it up into a bunch of smaller lines. Okay. So we're just going to draw a bunch of little nodes here, just like that. But the most important thing is not the fact that we drew kind of smaller lines here, but we need to label this. Okay, so each of the nodes that I drew here is going to be identified with an ID number. Okay. And so for this particular case, I was just kind of drawing somewhat randomly, and so we ended up with 10 nodes. Okay, so we have a 10 node domain. Okay. And remember, one thing that we're going to assume, and most of the time we're going to assume this just because it kind of makes our lives a little bit easier. We're going to assume that each of the nodes in our domain are equally spaced apart. Okay. And so the distance between two nodes, like say node 1 and node 2, we'll call that delta x. Okay. And so that delta x is going to be constant in between each of the nodes in our system. Okay. And so, you might ask the question of, how many nodes do we typically need to set this domain? Well, it depends. It kind of depends on the problem. So there's going to be some problems where you need to have a lot of nodes for an accurate solution. And there's going to be some nodes, there are some situations where you don't need that many. Okay? And so I kind of just drew one kind of somewhat generically now, but, when we actually do the example, we'll actually kind of draw the domain with actually, I think, only 6 nodes. And so, the first thing we're going to do is just 6 nodes. But, just know that you can modify this. And so the idea is to kind of change the number of nodes based on the problem. Okay. All right. Any questions on this so far? Okay. All right. So that's the discretization of the domain. So once the domain has been discretized, the next step is going to be to discretize the equation itself. So let me write out the equation again. So that's kind of our generic kind of 1D diffusion equation. And so we want to discretize it. And when I say discretize, what I basically mean is that we're going to apply some kind of computational technique to transform this into an algebraic equation. Okay. And so for this first unit, that technique that we're going to apply is finite differences. And so we're going to apply finite differences. To all the derivatives. Right, so the only derivative we have here is that second order derivative, and so we're going to apply our central differencing scheme to that. Okay. And so if we apply our central differencing scheme, we get phi I minus 1 minus 2 phi I plus phi I plus 1, all divided by delta x squared. And then on the right-hand side, we have q sub I. Okay. So this q sub I, the reason I put a subscript of I there, basically what we're doing is we're going to evaluate our forcing function at that node I. Okay. And once we do the example later on, then you'll kind of see what I mean by that. All right. So now we have two things. And so we have our discretized domain, which is our kind of our 1D line that's broken up into all of these little subdomains with the numbered nodes. And we have our discretized equation. Okay. And so our next step is to kind of merge these together. And the way that we're going to do that is we're basically going to apply this finite difference approximation to each node in our discretized domain. Okay. Okay. And so you'll see what's going to happen is that each time we apply, or each application, or each node that we apply this finite difference equation to, is going to give us one algebraic equation. Okay. And then so basically, the idea is that if we apply this to every single node in the domain, then we're going to have one equation per node. Okay. And then once we have that collection of equations, we can solve all of them together to solve for the solution values at each node. Okay. And so eventually we're going to get a situation like this. Let me go ahead and draw our domain again. Okay. And so at the end of this whole thing, so once we solve the equation for each node, we're going to have a corresponding solution value. Okay. So let me draw it so you can kind of visualize it better. I'm just going to make these arrows a bit bigger. And so at node 1, we're going to have the solution value phi1. Node 2 is going to be phi2, phi3, phi4, phi5, phi6, phi7, 8, 9, 10. Okay. So our goal is basically for every node in the mesh, we're going to solve for the value of the solution at those nodes. Okay. And then if you want, you can plot them visually so you can kind of connect all these solutions together. But maybe you can do a better job than I did, trying to draw a line going from left to right. And then you can actually plot the solution. Okay. Any questions on any of this? Okay, all right, so let's put this in action to using the example that we did before, just so you can see all of this kind of happening at once. Okay. All right, so for this example, let's do the same problems. We have d squared phi dx squared is equal to 6x. Okay, that was the equation that we solved exactly last time. And we have the boundary conditions. Phi of 0 is equal to 1, and d phi dx. X is equal to 1, it's equal to 0. Okay. And so what we want to do is we want to take this equation and solve it via finite differences. And we're going to do that on a grid of 6 points. Okay. So let me just go ahead and draw our domain here. One, two, three, 4, 5, 6. Okay. We know that the left side of the domain, its x coordinate is 0. The right side of the domain, its x coordinate is 1. Okay. And so this is the domain that we want to solve our system on. All right, so the first thing we're going to do is, now that we know how many grid points that we have 6 grid points, and we know the size of the domain, the size goes from 0 to 1. Let's compute the grid spacing for this system. All right, and so we have 6 nodes. And so if we have 6 nodes, that means we have 5 kind of spaces, right? So we have 1, or I'll call this A, space A, B, C, D, E, okay? So the 6 nodes defines 5 different spaces between the left side and the right. And so our grid spacing, delta x, if we assume that it's uniform all throughout, so all the grid spacings are the same, is going to be the length of the domain, capital L, grid spacing is going to be the length of the domain divided by big N being the number of spaces in the domain. Okay. And so for this problem, the length of our domain, if we take the difference in the x coordinates, and so we do 1 minus 0, the length is going to be equal to 1. Okay. and the number of spaces here is 5. So we have 1 divided by 5. That tells us our grid spacing here is 0.2. Another way you can do this, if counting the spaces, is a little bit weird. I know it's kind of a weird way to do it. Another way that you can compute the grid spacing is you can take the length of the domain divided by little n minus 1. Or little n right here, little n is the number of nodes in the grid. And so we do the same thing. And so the number of nodes that we have here is 6. And so we have 1 divided by 6 minus 1. And so we get the same thing, which is 0.2. Okay. So either equation for the grid spacing works. It's just, whichever is kind of more comfortable for you to do. Okay. Any questions on this? All right, pretty straightforward so far. All right, so now we need to apply finite differences. Okay, so we want to find the finite difference solution. Okay. And so since we have 6 nodes in this system, okay, remember our goal is to solve for the solution value of each of those 6 nodes. Okay. And so to get 6 solution values, 6 nodes, that means we need 6 equations. Okay. All right, so let me go ahead and write our equation again. So our equation for this example problem is d squared phi dx squared is equal to 6x. Okay. Let me go ahead and apply finite differences to it. So let me go ahead and replace the derivative with a finite difference. And so if we replace the second order derivative with a finite difference, then we get this equation right here. I'm going to go ahead and simplify this a little bit just because the fractions it's a little bit hard to kind of rewrite this over and over again. And, we are going to write this equation a lot. And so I'm going to take this delta x squared and just multiply it by both sides. And so we end up with the following. So phi I minus 1 minus 2 phi I is equal to, plus, it should be a plus right here. Sorry about that. Plus phi I plus 1 is equal to 6xi delta x squared. I'll underline this just because we're going to be applying it a lot, but it's not going to be the final equation that we have. Because what we're going to do is we're going to apply this equation to every node or every node that we can. So we're not going to be able to apply this to every single node, and you'll find out why very soon. But for all the ones that we can apply it to, we'll apply it to those nodes. Okay. Okay, so let's start with the first node in the system. So the first node in the system is I is equal to 1. Okay. Okay, so remember our first node has I is equal to 1, and that goes up to 6. Okay. So we start at I is equal to 1. Let's go ahead and apply our equation to this. And so we have phi I minus 1. So 1 minus 1 is 0. Minus 2 phi I minus 2 phi 1 plus phi I plus 1. Phi I plus 1 is 2 in this case. And then we have, and this is going to be equal to 6 times 6, or it's going to be equal to 6 times the x coordinate xi. Xi in this case is the x coordinate of the first node. And so this is going to be 0. Okay, so that's the reason why that there's 0 there. And we're multiplied by delta x squared. We know delta x from earlier. Delta x is 0.2. And so we're going to multiply this by 0.2 squared. Okay. All right. So that's our first equation. So that's the first application of finite differences. Okay. But we have a problem here. And so, you know, what's the main issue with this equation that we just wrote? It's this guy, right? So in order to use this equation, we need to have the value phi 0. Okay. If we look at our domain, there is no node 0. The leftmost node here is node 1. And so in order to apply this equation, we would have to basically try to obtain a phi value that doesn't exist. Okay. And so since you know we have a phi value here that's invalid, so that's kind of another way you can say it. You can say that that phi value is invalid. We cannot use this equation. At I is equal to 1. Okay. And so I'm just going to draw a big X through it. We'll come back to I is equal to 1 later. Basically, what we're going to apply there is a boundary condition. Okay. But in general, what you'll find out is that, you know, when you're doing these finite difference solutions, especially in the homework as well, you can't apply the finite difference equation to the boundary nodes. And so the nodes that are sitting on the left or the right boundary, and in 2D, the top and bottom boundary as well, you need to do something different at those nodes. All right, any questions on this? Okay. All right, we'll come back to I is equal to 1. But for now, let's just go ahead and move on. All right, so let's apply the same equation for I is equal to 2. Okay. All right, so same equation. So we have phi I minus 1. So phi I minus 1 is phi 1. Okay. Minus 2 times phi I. Phi I in this case is phi 2. Plus phi I plus 1, which is phi 3, is equal to 6. Then we multiply by xi. Xi in this case is the x coordinate at I is equal to 2. So that's going to be 0.2. Okay. And we multiply by delta x squared, which is 0.2 squared. Okay. All right, so let's look at this equation. And let's check for any invalid phi values first. Okay, so that was something that kind of prevented us from using the previous one. Okay. All right, so first we have phi 1. And so we look here, do we have a node 1? We do have a node 1, right? And so phi 1 is fine. Next we have minus 2 phi 2. And so we check back out our domain. Do we have a node 2? Yes, we have a node 2, so that's all good. And then we check for node 3. Okay, phi 3, do we have a node 3 in this domain? Yes, we do. And so all the phi values are good. So actually this equation here is going to be valid, you know, just fine. Okay. Right. And so since that one's good, we can go ahead and move on to the next I value. So this is exciting. So this is, you know, our first equation here. Remember, we need 6 of them overall, and so this is our first. All right, so next we're going to apply the same finite difference equation here, but we're going to set I is equal to 3 instead. Okay. All right, I'm gonna go a little bit faster just because, you know, this is kind of the same thing over and over again. And so if we apply the same equation at I is equal to 3, we get phi2 minus 2 phi3 plus phi4 is equal to 6 times 0.4 times 0.2 squared. Okay. And then what you can do is you can check all the values, and all these are valid nodes. So this is also a valid equation. Okay, so let's do the same thing at I is equal to 4. And so we plug in I is equal to 4, we get phi3 minus 2 phi4 plus phi5. And this is equal to 6 times 0.6 times 0.2 squared. Okay. And again, all of these are valid nodes. And so this is all good to go. Okay. And then finally, we're going to apply it at I is equal to 5. And so we apply it at I is equal to 5, we get 0.4 or phi4 minus 2 times phi5 plus phi6 is equal to 6 times 0.8 times 0.2 squared. Okay. All right, any questions on these 4 equations? So this one's also valid. All right, so we have 4 equations. So we have 4 out of the 6 equations. Let's try applying the same finite difference equation to I is equal to 6, and let's see what happens. Right. So we apply the same finite difference equation to I is equal to 6, and we get phi5 minus 2 phi6 plus phi7 is equal to 6 times 1 times 0.2 squared. Okay. And just like we did at I is equal to 1, we have an issue with this last equation right here. Okay. Node 7 does not exist, right? And so in order to use this equation, we would need phi7, but that doesn't exist in our domain. And so just like we did at node 1, we're going to cross this one out right here because we can't use this equation. Okay. And so what we've done so far is that we've taken our original equation, we discretize it using finite differences, and then the resulting equation we applied to all of the, I call them interior nodes. Okay, so they're interior because they're not on the boundary. And what that's given us is 4 out of the 6 equations that we need to solve this system. Okay. And so for the remaining nodes, okay, the remaining nodes being I is equal to 1 and I is equal to 6, let's use the boundary conditions to get these equations. Okay. And that makes sense because these nodes are on the boundaries. And so their behavior should be governed by the boundary conditions. Okay. So let me write down our two boundary conditions again. And then, let's see how we can turn them into an actual equation. All right, so our first boundary condition is fairly straightforward. Our first boundary condition was phi of 0 is equal to 1. Okay. And so let me kind of explain or kind of write down or describe this boundary condition in words. Okay. And so what this is basically saying is that the value of phi n x is equal to 0 is 1. Okay. All right, how can we encapsulate this into a boundary condition? So let's go back to our domain. And so here's our domain here. Let me write in the phi values. And then just for clarity as well, let me go ahead and write in the all the x values as well. Right, so every node in our system has its own physical coordinate. It has its own x value, and each one has a corresponding phi value that we're going to solve for. Okay. All right. And so when we look at our boundary condition, what that's saying is that the value of phi at x is equal to 0 has to equal to 1. Okay. Let's look at our domain here and let's find the place where x is equal to 0. Okay. And so we know that when x is equal to 0, we're talking about node 1, right? So node 1 is physically situated at x is equal to 0. All right, so let's use that information to kind of form our boundary condition. Okay. Okay. And so when x is equal to 0, that means we're at node 1. And if the value at phi at node 1 has to be 1, and so we put those two pieces of information together. This tells us that phi 1 has to equal to 1. Bless you. And so this very simple equation right here, I know I kind of talked around it for a long time, something that maybe was very obvious, but this equation here is telling us that phi 1 is equal to 1 according to the boundary condition. Okay? And so this is going to be our I is equal to 1 equation, right? And so instead of using our finite difference equation that we had above, we're going to be using this equation here instead. Okay? Right. Any questions on this? All right, so that's the I is equal to 1 equation. And so, we can say this is crossed off. Now we need an equation for I is equal to 6. Okay. And so let's look at our other boundary condition, our boundary condition on the other side. And so our boundary condition on the other side is d phi dx at x is equal to 1 is equal to 0. Okay. And so if I describe this in words, this basically says that the derivative of the solution at the end of the domain is equal to 0. Okay. All right. And so we're going to treat this boundary condition a little bit differently. And so because it's not a direct specification of the solution, we have a derivative. Okay. And whenever we have a derivative, remember the thing that we like to do is we like to transform this using finite differences. Okay. Well, we have to be careful here because remember, we're at the end of the domain. And so we don't want to run over the side of the domain. Okay. We want to make sure that we kind of stay within the nodes of the domain. And so if you remember for a first order derivative, we have 3 options here. Okay, so we can either do a central difference, at I is equal to 6. Okay. We can do a forward difference at I is equal to 6. Or we can do a backward difference at I is equal to 6. Okay. And so for a first order derivative, those are our three options. Okay. And so at this point, it's almost like a puzzle. And so our confines are that we need to stay in the bounds of the domain, and here are your 3 kind of options to do so. Okay. All right, so let me apply each of those differencing schemes, and then you can see which one is going to be the most valid. Okay, so let's start with central difference, and so I'll call this CD. Okay. And so central difference, remember we take the neighbor to the right minus the neighbor to the left, and we divide it by 2 delta x. Okay. And so if we apply this at I is equal to 6, we get phi 7 minus phi 5, divided by 2 delta x. So let's look at the forward difference. And so forward difference is phi I plus 1 minus phi I is equal to, or divided by delta x. Okay. Okay. And then finally, we have the backward difference. So backward difference, we have phi I minus 1 divided by delta x. Okay. So phi 6 minus phi 5, all divided by delta x. So hopefully from this, it's pretty clear which one we should choose. Okay, so basically anything with phi 7 we can't choose because phi 7, remember, does not exist. Okay, so here we have phi 7, so we can't use central difference. Here we have phi 7, we can't use central difference, or forward difference, sorry. And so the only option that we have here is the backward difference, which takes into account phi 6 and its left neighbor phi 5. Okay. All right, so let's replace the derivative in the boundary condition. With this. Okay. And so remember, our boundary condition is d phi dx at x is equal to 1 is equal to 0. Okay. If we replace that derivative with our finite difference here, we get phi 6 minus phi 5 divided by delta x is equal to 0. Okay. In this particular case, since our boundary condition here is equal to 0, we can multiply both sides by delta x just to cancel it out, just to kind of simplify our math. And so we get our final equation here. We have phi6 minus phi5 is equal to 0. And so that gives us our 6th and final equation, okay, that we need to solve. Right, any questions on how we obtain this this equation here? Okay. All right. And another bit of trivia, before we kind of put it all together, remember, I picked these two boundary conditions on purpose so that you kind of see both. Okay? So the first boundary condition here, where we have we specify the solution directly. Remember, this is called a Dirichlet boundary condition, or Dirichlet. Actually, I have no idea how you pronounce it. I've never met the guy. Okay. And the second boundary condition, where we have a derivative boundary condition, remember that's called a Neumann boundary condition. Okay. And so you'll hear me use that terminology throughout the course. And so, just kind of remember what they are. Okay. But it's kind of nice because, you can see that depending on the nature of the boundary condition, whether it's kind of a Dirichlet boundary condition or a Neumann, we have to treat them differently. Okay, so the way that we obtain the equation for that boundary condition depends on the type of boundary condition. So it's kind of useful to have different names for them, just so we know that we know how to treat them. Right, and so just like Thanos in Infinity War, we've assembled all of the equations that we need to. Okay, except instead of stones, we have equations which are not nearly as fun, but we'll make do with our best. Okay. All right, so let's go ahead and assemble all our equations so you can kind of see them all at once. Okay. Okay, so our 6 equations, remember, they refer to each of the 6 I values. Okay, so we have I is equal to 1, 2, 3, 4, 5, 6. And so let's write out our equations for each. Okay. So let's start with I is equal to 1. So our I is equal to 1 equation that came from our Dirichlet boundary condition. And so this is simply phi1 is equal to 1. Okay. Our equations for I is equal to 2, 3, 4, and 5. These came from our finite difference approximation of our governing differential equation. Okay, so let's go ahead and write these down again. So I'm just gonna write these down kind of fairly quickly, and so I'll give you time later to kind of catch up, but just for the sake of time, I want to make sure that we have enough time to do the math. Okay. And so those 4 equations in the middle, I, 2, 3, 4, and 5, those are kind of the longer ones because those came from the differential equation. Okay. And then finally, we have I is equal to 6, which we just obtained up here. And so let's go ahead and write that equation in. So we have, and I'm gonna swap the order of the terms just to kind of make it consistent with the rest of the ordering. And so you have minus phi5 plus phi6 is equal to 0. Okay. Right. And so we did it. And so, we have our 6 equations here, and we're going to use them to solve for our 6 unknowns. And so our 6 unknowns being phi1, phi2, phi3, phi4, phi5, and phi6. Okay. All right. So in theory, you could solve this equation by hand. You can solve this system of equations by hand. Okay. And this one's actually not horrible. It is a pain, but technically you can do this by hand. It would probably only take you maybe half an hour. Okay. Right. But we're not about that life in this class. We're not about doing a linear algebra by hand. And so what we really want to do is we want to have the computer solve this for us. Okay. And so, but in order to do that, we have to put this into a form that the computer can actually solve. And so let's go ahead and take this linear system of equations and put it in matrix form. So this is like problem 2 on the first homework. Okay. All right, so here's our matrix system of equations. So let's go ahead and plug in the values based on our system of equations here. Okay. And so our first row is just phi1 is equal to 1. And so that means we're gonna have a 1 on the phi1 term, and zeros everywhere else. And on the right-hand side, we're gonna have a 1 there. Okay. Our second row is going to be 1 minus 2, 1, 0, 0, 0. Okay. Our third row is going to be 0, 1 minus 2, 1, 0, 0. Okay. Our fourth row is going to continue on with that pattern. And then our last row is just 0, 0, 0, 0, minus 1, 1 is equal to 0. Okay. All right. Any questions on how we obtain this this matrix here? So remember, we're just extracting the coefficients out from the system of equations and just putting them into our matrix. Okay. All right. And so for the last 20 minutes, let's talk about how we actually implement this in MATLAB. Okay. And we're going to do it 2 ways. And so we're going to do it kind of I call it the brute force way. And so we're just going to basically implement this matrix kind of just by hand. And then I'll kind of start you guys out on how to make this code more adaptable. Okay. All right, so let me go ahead and swap to the computer here. And let me open up MATLAB. That would certainly help. Okay. All right, so let me go ahead and create a new script just so we can save this. Okay, and so basically we want to write the code here to solve our finite difference problem that we started. And so primarily what we want to do is we want to populate the left-hand side matrix and the right-hand side vector. Okay. And so if you look back on your notes, you know, there was a matrix that we had, and there was a right-hand side vector. And so we want to code those into MATLAB. Okay. We want to do it in kind of a smart way where we can kind of extend this code and modify it for the future. Okay. Actually, let me go ahead and bring this out just so I can kind of full screen it. Okay. All right, so first thing we're going to do is we have our domain. Okay. And so let's create a vector. Let's create a vector that's going to store the position values for each position values for each node in our domain. Okay. Okay. And so if I draw the domain again, okay. Remember the way that we did this domain is we had 6 nodes, right? And then the spacing in between each of the nodes was 0.2. And so that means the position of node 1 is 0, the position of node 2 is 0.2, 0.4, 0.6, 0.8, and 1.0. Okay. All right, so I'm going to use, let's create a vector. So I'm going to call it pos vector. Okay. And this pos vector is going to contain the values for each of the nodes. Okay, so let me go ahead and use a tool. So remember this from last week, we learned about this special command called linspace. And so the way linspace works is that we give it a starting value, an ending value, and the number of points that we want. Okay. And so in this case, our starting value is going to be 0 because that is the left side of the domain. The right side of the domain is 1, and so that's going to give us the ending value. And then the number of entries in this vector is going to be 6. And so let's go ahead and do just that. Okay. All right, so let me go ahead and run this code. For some reason, it's not letting me run it. Oh, okay. It's not letting me run it because I started with a number. Okay. Okay, so I went ahead and ran the code. All right, and so if we look at the values of pos vector, let me go ahead and eliminate my drawings here. You can see that pos vector has the x values for each of the nodes in our domain. So our first value here is 0, then it goes up by 0.2 from there. So 0.0, 0.2, 0.4, 0.6, 0.8, and 1.0. All right, so that's going to be useful because you know, if you kind of look back at your notes, I didn't actually compute the right-hand side vector, so you know that's going to be useful for us to do that. Okay. So next thing we're going to do. So next, let's create a variable that is going to store our grid spacing. All right, and so I'll call this value dx. And so this is going to be a fairly simple case. Okay. And so our grid spacing is a constant value in this case. And so our grid spacing is just 0.2. All right. So now that we have the position vector, we know the positions of each node in our domain. We have a variable that's going to store our grid spacing. Now let's start assembling the equations. All right, so the first thing we're going to do is we're going to create empty vectors. Okay, so we're going to start by creating an empty left-hand side matrix and an empty right-hand side vector. Okay, so remember the way that we create empty vectors is that we use the zeros command. Okay, and so I'm going to create two variables here. So we're going to have left-hand side matrix, okay, is equal to zeros. Okay. And if we look at the size of our matrix here, we actually have six rows and 6 columns. And so this is going to be 6, 6. Okay. And our right-hand side vector is a column vector. And so it's going to be 0, 6, 1. Okay. So now that we have all the empty vectors assembled, let's go ahead and start filling in the values. Okay, so let's do it one equation at a time. And so we do I is equal to 1. Okay. If we look back at our matrix, okay, so if you look back at your notes, the first row of the matrix is just a 1 on the diagonal. Okay. We have left-hand side matrix at 1, 1. This is equal to 1. Then the right-hand side vector at 1 is equal to 1. Okay. All right. So that's our first row of the equation. Let's work on row 2. Okay. And so if we go to row 2, in our matrix, we have 3 entries in the left-hand side matrix. Okay, so we have left-hand side matrix, left-hand side matrix, left-hand side matrix. Okay. They're all going to be in row 2. So 2, 2, 2, All right, so let's start with the leftmost entry in row 2. And so if we look at the pattern for row 2 of the matrix looks like this. So we have 1, -2, 1, 0, 0, 0. Okay. Right. So remember, for the zeros, we don't have to do anything because remember our matrix is already starting at zeros. And so we only have to worry about the non-zero entries. Okay. And so the entry at 2, 1 is going to be 1. Okay. The entry next to it at 2, 2 is going to be -2. And the entry after that at 2, 3 is also going to be 1. Okay. And then we come up to the right-hand side vector at x is equal, or at node 2. Okay. This is equal to 6 times x2. Remember, the way that we obtain x2 here is pos vector at 2 multiplied by dx times dx. Okay. So this right here, this is 6 times x2 times delta x squared. Okay. And so if you look back in your notes on the right-hand side of the equation, at the right-hand side vector for that second row, that's exactly kind of what we have over there. Okay. All right, any questions on this so far? Okay. Oh, question? All right, question. So is there an advantage of filling our matrix like this when we don't use looping versus typing the matrix like that? Yeah, that's a good point. And so if you are just going to kind of specify the matrix kind of just by hand like this, you can just do it kind of directly using the square bracket notation. But the reason I'm doing this is that eventually we are going to turn it into a loop. And so yeah, that's kind of the main reason I'm doing this. Yeah. Okay. And so let's write the code for I is equal to 3. Right. And so the nice thing about all the interior nodes is that they have kind of the same pattern. It's just that everything is shifted over by 1. Okay, so what I'm going to do is I'm going to take the code for I is equal to 2. I'm going to paste it, but I'm going to shift everything over by 1. And so we're going to have 3, 3, 3, and then 2, 3, 4, and then 3, and 3. Okay. All right, so everyone kind of see how I did that. So I just kind of copied and pasted the code, and everywhere there was an index in the matrix, I just shifted it up by 1. Okay, both, not only for the left-hand side matrix, also for the right-hand side vector and the pos vector as well. Okay. All right, so I'm going to go ahead and copy this, and we're going to do 2 more times. So we're going to do it for I is equal to 4. So let's go ahead and do that. 4, 4, 4, 4. 3, 4, 5, 4, 4. Okay. And then I'm going to do the same thing for I is equal to 5. So I'm just going to copy, same thing. Okay. We're going to do 5, 5, 5, 4, 5, 6. And then 5. Okay. I know I'm going a little bit fast just because I want to make sure I finish this and then start the loop. At least kind of give you some hints on how to start the loop part, because that is the first problem on the next homework. Okay. But feel free to go back and look at this recording afterwards if you kind of need help writing this out. Okay, and then finally we have I is equal to 6. And so for the last row of the matrix, we only have 2 entries. Because we have left-hand side matrix at 6, 5 is equal to -1. Left-hand side matrix at 6, 6 is equal to 1. And then right-hand side vector at 6 is equal to 0. Okay. Technically, I guess you didn't need to do that last one because the right-hand side vector started out as 0, but you can kind of do it just for completion. All right. Any questions on this? Okay. All right. And so we're just about done. And so now that we have the left-hand side matrix and the right-hand side vector specified, okay, and so to solve the equation, it's actually just one line of code. It's actually pretty nice. Okay. And so this is also just like problem 2 in the homework. And so what you're going to do is you're just going to do left-hand side matrix / right-hand side vector. So let's go ahead and run this code. You come back here, you now have a solution vector, and it looks just like this. Okay. All right, so you don't have to type this next part. I'm just going to go kind of fairly quickly here. Okay. And so what I'm going to do is I'm going to compare this to the exact solution. Okay. So I'm just going to go pretty fast here. Okay, so this is mostly just so that you can see it, but I know I am going kind of fast here. Okay. All right, so let me go ahead and run this. Okay. And so from this graph right here, it's a little bit, maybe I should have labeled it before I plotted it. But basically what we have here is that, in the red right here is the exact solution. Okay, so that's the exact solution that we obtained by solving this equation by hand. And then in the blue, we have the finite difference solution. Okay, so finite difference, it didn't do a bad job. Okay, so obviously it's not fully correct yet because it's only 6 nodes. Okay, so 6 nodes is fairly coarse, and so it's hard to get kind of an exact solution with 6 nodes. But at least it follows the same kind of general path, right? So we're kind of on the right track. Okay. All right, and so what you should see is that if we took this solution and instead of 6 nodes, we increase the amount of nodes to say like 50, then you'll see that this solution here actually gets much closer to the exact solution. Okay. All right. All right, it's 1 more minute. I don't really want to cram the for loop stuff into 1 minute. So maybe we'll start with that in the next class session. Okay. Okay. Any final questions on this before we wrap it up for today? Okay. All right, so that was kind of our first code together. I know we did it kind of fast, and so what I'll do is let me save this code. What I'll do is I'll upload this code onto Canvas, and so if you wanted to take a look at this code, and then what we'll do on Monday is that we'll open up this code first thing, and then we'll talk a little bit about how you can kind of make this more general and modify the number of nodes in real time. Okay. And what you should see on Monday is that as we change the number of nodes, as we increase it from 6 to 10 to 20 to 25, then our finite difference solution here in the blue, it should get a lot closer to the exact solution. Okay. All right, so thank you guys for coming today. I know the MATLAB went kind of fast, and so we'll do this again on Monday. But hope you guys have a good weekend. Keep an eye out for homework 2. So homework 2, I think, will be posted by tomorrow. And then we'll go from there. Right. So hope you guys have a good weekend, and I will see you guys next week. Hey, Dominic, have a good weekend. You too.
Yeah. Values for the I don't know what the word is. The matrix at the end after the sign, because I just want to. Oh, you didn't count. Okay.
Yeah. I actually like that on purpose because normally, for MATLAB stuff, you kind of leave it form.